Today we will start new unit called Theory of Fundamental Load Compensation. So here we will talk about and explore the methods through which we compensate the unbalance in the load currents, and also we will regulate the bus voltage. So there are two aspects. Number one is the power factor correction, or you can say the reactive power injection, or you can say the load compensation, and the second aspect is the voltage regulation. If you wanted to speak in terms of the voltage and currents, so basically there are two kinds of compensation. Number one, the current compensation and the voltage compensation. Okay, the current compensation is referred as the load compensation, and the voltage compensation is basically called the voltage regulation in the power system. Now we have learned earlier that the loads are maybe of different types in three-phase system. For example, it could be the unbalanced AC load. Balance is very common anyway. Okay, so unbalanced AC load is what is problematic, and then we have an unbalanced AC plus nonlinear load, and then we have unbalanced AC plus nonlinear plus DC load. So these are the three main classification of different types of load that creates problem in the power system. That is unbalanced AC, then unbalanced AC plus nonlinear, and unbalanced AC plus nonlinear plus DC. Now here we use the term fundamental load compensation, and fundamental load basically means that the load is consisting of RLC linear elements. That ensures that if the voltages are fundamental, the current should be also fundamental. That is, they do not create any harmonics. So first we will start with the fundamental load compensation, and then we extend the ideas to any type of load compensation. So let us consider the power system where we represent the load bus with this B here, and this is connected to the load shown in this figure here, which requires current IL. Okay, so this load you can write either in form of ZL, or you can write as YL, whatever you prefer. We can write in any of these forms, and of course YL is same as 1 by ZL. So for this impedance, the current drawn is IL. The current from the source is IS. Now what is the source? The source is the upstream voltage line. So this could be ES. This is E, or you can say upstream voltage source. Now here E is same as B. Okay, because the line that we have assumed is basically ideal line which has zero resistance and zero reactance. Therefore E is equal to B. But if this line has a feeder impedance, then E is not equal to B. So in this particular case, this is called stiff voltage source. That is, there is no reactance of the line. And also IS equal to IR, or IS equal to IL. The source current is same as load current because there is no other parallel path here. Okay, so we can represent the voltage as reference voltage, that is V equals to B angle of 0, and I is equal to I angle of phi L. Let us say the current is having angle of phi L. The phi L could be negative for lagging and could be positive for leading. Okay, and this is shown here. This is the reference voltage here, B, and this is the current I, which has angle of phi L. Actually, I have taken phi L lagging. That means this phi should be negative actually. The value of phi L is negative. That's all I am saying. Okay, so assume that, let us say, phi L is equal to minus 30 degree. In that case, this is the situation that current lags the voltage by 30 degree. Let us find out the current that flows through the load. So current is given by B into admittance, B into by L. This is the voltage, and this is actually grounded. So this is zero potential, this is B potential. So the current that will flow in the load is B into by L. So this is B here, and this is the by L. Now remember, this by L is actually 1 by ZL. So if you have parameter like this, 1 by RL plus JXL, then it becomes R minus JXL by RL square plus XL square root. Okay, square, yeah. We multiply both sides with the complex conjugate of this term. So you will get this term, which actually means that is RL by RL square plus XL square and minus, or you can say plus J minus XL by RL square plus XL square, which actually means this is GL plus JBL. So same form we have written here, GL plus BL. I have used small l here, capital U, you can change it, that is up to you, you can use both of them. Okay, so what is GL? GL is nothing but, in terms of series resistance, it is RL by RL square plus XL square. If this consists of, let us say, RL, for example, then this is the value of GL and this is the value of BL. BL is negative for inductive circuit, or susceptance of the inductance is negative, minus XL by RL square plus XL square. Okay, so this is the BL. So in terms of GL and BL, we can write this by as a GL plus JBL, and if you want to express in terms of the series impedance, then it can be expressed using these expressions. Now we expand this bracket, we'll get B into GL plus JB into BL. These are scalars because B is the reference potential or reference voltage, so this is kind of a scalar values, and therefore we can write as in phase component IR plus JIX, because this I is in phase with the B, it has no phase angle, this angle is 0. Okay, this is just a scalar value, so we can call it in phase component, and this is J here, so J means this is phase quadrature component. You can see it here, this is IR, and the perpendicular to this is basically IX, so this is JIX, which you can take angle of this, that is sine phi L. So we can also express this component in terms of the IL and the phi L angle. This IR becomes IL cos phi L in phase component. If I take the projection of this line, okay, along with the horizontal axis, then it is IR. And if I take the projection of this along the vertical axis, this is IX. So we can write therefore IR equals to IL cos phi L and IX equals to IL sin phi L. Is that clear? Okay. Now with this understanding, let us express the load power. The load power, since we know the current and voltage across the load, we know the voltage at the bus and we know the current flowing through the bus, then we can express in terms of the apparent power. So SL bar means complex apparent power is actually B into IL conjugate. You know about this term. Any complex power is given by B into I conjugate. So if I want to find out the apparent power at the load bus or at the load, then it is B into IL conjugate. So what is B? B is reference voltage, B angle 0. So this is B angle 0. And what is IL? IL is IL angle of phi L. And conjugate of this, it becomes B into IL cos phi L minus JBL into IL into sin phi L. Clear? So this is the real part and this is the imaginary part of the SL. So obviously this must be PL plus JQL. That's how the complex apparent power is. It is the real power plus J reactive power. So this must be PL and minus BIL sin phi L must be QL. As you can see here from this expression, this is the PL, this is the QL. We can also express in terms of the B and the components of current in phase and quadrature, that is IR and IX. Since we know that IL cos phi L is IR, so this is BIR here minus J B into IX, which is same as BIL cos phi L and BIL sin phi L, and which can be written as SL cos phi L. See, this is SL scalar. This is SL scalar and the angle is phi L, as you can see from here. So obviously it must be nothing but SL cos phi L, if this, and this is minus SL sin phi L. Actually if you look this term here, so B is same as B because a reference phasor, and then IL and angle phi L minus, this is actually SL complex. That becomes BI cos phi L minus JBI sin phi L. That's what you see it here. So now we learned that the PL and QL can be expressed in terms of the B and I or SL, the scalar value, through the phase angle phi L. Now let us express this power in terms of the voltage. So voltage, if we express, then we use the same expression, SL equals to B into IL conjugate. This is B reference phasor. IL is BGL plus JBBL conjugate. We just proved earlier the value of IL is nothing but B into bi. So if we substitute the value of IL in terms of BGL here, the same thing as this. If you look this value, B into GL plus J into BL, this value of IL. Then we will get BGL plus JBL conjugate. And conjugate basically means minus J. So this becomes B into B, that is B square GL, the first term, minus is here, and then J, then B square BL. That means this is PL and this is QL. So PL actually means that B square GL. So we can write PL equals to B square GL and QL equals to minus B square BL. These are the real and reactive powers at the load bus. Okay. Now with this understanding, we will proceed further with the scheme of the reactive power compensator. That is, if we want to compensate the real power, reactive power, or we want to improve the power factor, then we need to place the compensator. Correct? The whole idea is this, that the compensator should be placed in shunt with the load so that it cancels the reactive power component of the power. For example, this is the load and this has two components as we just have proved it. Okay, it has two components, number one the real power and second the reactive power. So earlier we have said this SL equals to PL plus JQL. This QL is unnecessary component being taken from the supply here. We don't want to take from the supply. We don't want to take it from the distribution line or transmission line. It means that we want to compensate it locally like this. So this Q will be supplied from compensator S gamma. Okay, so let there be compensator which is connected at the load bus, and this takes care of the reactive power compensation. So with this compensator, what will be the compensator current? The nature of this compensator is purely reactive network. It must consist of purely reactive network. Why it is so? If this is not purely reactive network, it will consume the real power, which is not a desired component of the compensator design. So let us say this compensator has admittance of Y gamma. Then the current that is flowing into the compensator is nothing but V into Y gamma. And Y gamma can be written as G gamma plus JB gamma. That is the conductance of that compensator plus the susceptance of the compensator. Now as I said, this compensator is purely reactive network, and therefore the real part of admittance is equals to 0, or you can say its resistance is infinite. So when G gamma equals to 0, this I gamma becomes simply JB gamma, because this is 0. So this is gone. So we have only B JB gamma. Okay, this is the value of the current. Or you can say IR, some magnitude whose value is B into V gamma and angle of 90 degree. This is quite obvious because this should be the phase quadrature component to supply the reactive power. That's why it is having 90 degree angle with this voltage. That ensures that it is the either 90 degree leading or lagging with respect to the reference voltage. Now what should be our target? Our target must be to compensate the load in such a way that the source supplies only the real power, not the reactive power. Okay, so this is the main function of the load compensation, in which the net current at the load bus, called IS, is sum of IL plus I gamma. This is the current of the compensator and this is the current of the load. So together I gamma plus IL becomes net IS, which is here. That's fine. So if we add them together, we will get IR plus JIX plus JI gamma, and IR is here JIX plus I gamma. Therefore, the reactive component is IX plus I gamma. Now, if we want this component to be 0, then I gamma must be equal to minus IX. This is an important condition. I gamma must be equal to minus IX. And what is IX? IX, we proved it, minus B into BL. You can see here. This is IL. IL is nothing but B into BL. Okay, but here if you see the sign, it is minus IX. So IX was B into BL. Therefore, the minus IX becomes minus B into BL. This is B into BL. Therefore, minus IX becomes B into BL. So you can see here that IX not I gamma equal to minus BBL actually. So this should be I gamma equals to minus J B BL, which is same as J into I gamma. Now we find out the apparent power of the compensator. S gamma can be found by using BI complex conjugate expression. The load bus voltage is same for compensator, for load. Therefore, the value of the complex compensator power is B into I gamma conjugate. I gamma just we find out minus J B into BL, conjugate of that becomes plus J. Okay, so it becomes J here and then B square, because B is here, B square BBL, which is actually P gamma plus JQ gamma. Since there is no real part, so P gamma equals to 0, which is very obvious because we don't have any resistance in the compensator. Or you can say, we directly compare this equation S gamma equals to P gamma plus JQ gamma, then obviously P gamma equals to 0 and Q gamma equals to B square BL, because conjugate of minus J becomes plus J and becomes the B square BL, which is also equal to minus QL, because we just found earlier that QL equals to minus B square BL. So this minus and this minus becomes plus, and finally we have B square BL. So this is the reactive power at the compensator. If we express in terms of the SL, so what is QL? QL is SL sin phi L with negative sign because of conjugate term. So minus and this minus becomes plus, and finally we have SL into sin phi L. We can express the sin phi in terms of the cosine, and that becomes 1 minus cos square phi L square root of that. So finally we'll get the relationship between Q gamma and SL. The Q gamma equals SL into 1 minus cos square phi L, or you can say this is equal to SL square root 1 minus power factor at the load square. Okay, 1 minus power factor at the load square. But this is very interesting equation actually. It tells how the rating of the compensator is affected by the power factor of the load. If the cos phi L is 0, that means the phi L is 90 degree. So for a purely inductive or capacitive network, this Q gamma equal to SL. Because this is 0, cos 90 is 0. Therefore, Q gamma becomes SL. That actually means that it needs very high compensation or full compensation. If cos phi L is unity, if the cos phi L is unity, then what will happen? This becomes 1 minus 1, 0. So Q gamma is 0. So Q gamma, the reactive power for the compensator will be 0 if there is a unity power factor. That means that we do not need any compensation because the load is already resistive. And if the power factor is poor, then the Q gamma rating is more. So you can see when power factor varies from, let us say, 0 to 1, the need for Q gamma varies from, this is cos phi L. When cos phi L is 0, the Q gamma is SL. When cos phi is 1, Q gamma is 0. So 1 means unity power factor and hence does not need any compensation. 0 means does not need any compensation. When the power factor is 0, it needs full compensation. So there are two extreme cases. So why varying gamma? This gives us idea that why varying gamma we can compensate the power factor, as well as we can also influence the voltage regulation. These are two important aspects of power system: power factor correction, and number 2 is the voltage regulation. Actually, the power factor correction can also be called as current regulation. And voltage regulation is counterpart of that. Accordingly, there are two devices called shunt device and series device. The shunt devices are used to compensate current and the series devices are used to compensate the voltage. Now let us consider these two important points here and see. So this is a system where we are considering the feeder impedance. So this is a more practical case. In the previous discussion, we did not take the feeder impedance. So now we have a feeder impedance Zs equal to Rs plus Jxs, and the upstream voltage source is E, and the downstream, that is the load bus voltage, is B. This current is Is, this current is IL. So in the first case, Is equal to IL because there is no any other parallel path. The load is represented by YL, GL plus JBL, and overall apparent power is expressed as P plus JQ, where the values of P and Q were explained earlier. Now this can be shown as phasor diagram, as you can see on the right hand side. This is the voltage here and this is the current. Okay. Now since this current passes through the feeder is here, because of that there will be some drop across the feeder. So let the feeder resistance be R and X, Rs and Xs. Then the drop across the feeder will be R into IL. IL is same as Is in this case because it is a series circuit. So IL is same as Is. Therefore, the resistance drop is R into IL. This is the drop across the resistance feeder. Actually, it should be Rs. and this should be XS, because this is a drop. Okay, so this is RSIL and BXS into IL. If we join them together on vector basis, then we will get the value of E. Obviously, E is sum of this voltage plus this drop. So voltage at the load bus plus drop makes the voltage at the source bus. That is E. So this B, then IS, RS, IL, and then XS, IL makes the E. So once you see the E and B are different, there is a voltage regulation in the system. Am I correct? Because they are different values of voltages, so there will be some kind of a voltage change at the load bus, and hence the voltage regulation come into picture. The voltage regulation is defined as the difference of source voltage and the load voltage divided by the constant voltage, that is the source voltage, E minus P by E. And therefore E minus B is basically called as the voltage drop. So this can also be written as delta B by E, where delta B is nothing but E minus B, that is ZS into IL. Basically it is drop across the feeder. If you see the voltage drop here, this and this, okay, is nothing but E minus B. And this drop is nothing but this current IL, which is same as IS, okay, same as IS here. So this is IS, and hence the drop across the feeder will be ZS into IL, which is same as E minus B. So here I have shown that this delta B equals to ZS IL, which is nothing but E minus B. Now let us simplify this IL and other parameters in terms of the active and reactive powers of the load. As we have proved that BIL conjugate is the complex apparent power, and this is equal to PL plus JQL. From this we can find out what is the IL conjugate. So IL is nothing but PL plus JQL by B. So this IL can be obtained by taking the conjugate of this whole term, this term. Okay. So that becomes PL minus JQL. So this is the conjugate of this expression, PL minus JQL divided by B conjugate. Now B conjugate, B and B are same because B is a reference phasor, so it doesn't matter, and therefore we can write this current IL as PL minus JQL by B. Now this gives us that how we can express the current in terms of the powers, the real powers and the imaginary powers. This is very important expression because this will be used in further derivations. Now let us find out E minus B, which is the voltage regulation, which is equal to delta BR plus J delta BX, which is same as ZS into IL. And once we know the drop across the impedance or the feeder impedance, we can find out the E. So therefore E is given as B plus ZS into IL. B is the reference phasor and ZS is the feeder impedance, which is RS plus JXS, and IL is nothing but PL minus JQL by B from here. Substitute these values and simplify them, we will get the real part and imaginary part. The real part will be B plus, multiply these terms to get the real part, that will be RS into PL, the first one, plus XS into QL, j and minus j becomes minus j square becomes 1. So this becomes the real part. The imaginary part is Rs into QL, this one, and minus Xs into PL. J is common outside. So you see there are two parts again. The one is the real part and the second is the imaginary part. So B plus B. Actually this whole thing is delta V, feeder drop, which is nothing but Is into Zs. But if we combine these terms with the voltage, it becomes B plus delta Br plus J delta Bx, where Bx is the reactive component or in phase component of the voltage drop, and this is in phase component, R for real, X for imaginary. So from this expression we can find out the source voltage in terms of the load voltage and other parameters, that is E equals to, from this expression we can write down here that B is common, this is B square plus RSPL plus XS QL, and BS V square and RSPL are written together, and then this term. This is the real part. Then you have also XS QL. So XS QL has come here. Then comes imaginary part plus J RS QL minus XS PL. The whole thing by B. And this side is E, which can be written as E angle of delta with respect to B. So E into delta into B, this becomes EB delta equals to the real part and plus the imaginary part. If we take the real and imaginary part on the left hand side, we will get EB cos delta plus JEB sin delta. This is cos, this is sin. So obviously this must be equal to this and this must be equal to this. Okay, so if we square and add both the sides, we will get E square B square, because cos square delta plus sin square delta square root will be 1. By squaring and adding these two real imaginary parts, we will get E square B square equals to the whole thing is square of this, okay, and then square of this. If you square and add them together, then we will get this expression, that is B square plus RSPL square of this, then square of XS into QL square, that is the XS square QL square, and then twice of this and this, so twice of B square plus RSPL into XS QL, this is the square of this term, and then we will make a square of the next term, that is the this one here, this is RS square QL square plus XS square PL square minus 2 RS XS PL or QL. We see that this equation is quadratic in Q. This term will cancel with this. The remaining terms are RS square plus XS square QL square. We will combine these two terms together. Now once we square these terms, we will see that it forms the quadratic equation in QL. So you can see here this is QL square. So this together, this and this becomes the RS square plus XS square into QL square. Then there is a coefficient of QL which is 2B square XS. So 2B square XS becomes the coefficient of QL. So this is 2b square xs. And then there are remaining terms, that is this square plus this square minus this square. So you can see here, this is b square RSPL square, then plus xs square PL square, and minus this term E square V square equals to 0. Therefore, this equation is in quadratic form, where we can write like this, okay, where A is this coefficient, B is this coefficient, and C is this coefficient. So from this we can find out QL as minus B plus minus B square minus 4AC by 2A. But here question is different. The question is that what should be the rating of the compensator such that B get the desired voltage at the load bus. For example, the condition is that we want to maintain B equals to E. So for that, what is Q gamma? Let there be some value of Q gamma. Then this Q gamma plus QL becomes QS, the net power at the load bus, or you can say QL dash, the new QL. Then we substitute this new value of QS here in this expression and solve for it, for the condition that B becomes E. So we solve this equation again for QS, which includes the QL plus Q gamma, to regulate the bus voltage same as the source voltage. So since B is equal to E, so this becomes e to the power 4, and wherever there was QL becomes QS. So this is QS, this is QS, and this is the constant term, this is E4 term. So this becomes A QS square plus B QS plus C equals to 0. And we can solve for QS, that QS equal to minus B plus minus B square minus 4AC by 2A. There will be two values of QS. The least value will be chosen so that the rating of the compensator is minimum. So once we know this QS, we can solve for Q gamma, which is equal to QS minus QL. And then we can design the compensator for this rating. I will continue this discussion in the next class.